Think about your day for a second. You woke up, felt fresh air in your face as you walked out the door, encountered new colleagues and had great discussions and felt in awe when you found something new. But I bet there's something that you didn't think about today, something so close to home that you probably don't think about it very often at all. And that's that all those sensations, feelings, decisions, and actions are mediated by the computer in your head called your brain. Now, the brain may not look like much from the outside, a couple pounds of pinkish-gray flesh, amorphous, but the last 100 years of neuroscience have allowed us to zoom in on the brain and to see the intricacy of what lies within. And they've told us that this brain is an incredibly complicated circuit made out of hundreds of billions of cells called neurons. Now, unlike a human-designed computer, where there's a fairly small number of different parts, we know how they work because we humans designed them, the brain is made out of thousands of different kinds of cells, maybe tens of thousands. They come in different shapes, they're made out of different molecules, and they project and connect to different brain regions. And they also change different ways in different disease states. Just to make it concrete, there's a class of cells, a fairly small cell, an inhibitory cell that quiets its neighbors. It's one of the cells that seem to be atrophied in disorders like schizophrenia, called the basket cell. And this cell is one of the thousands of kinds of cell that we are learning about. New ones are being discovered every day. As just a second example, these pyramidal cells, large cells, they can span a significant fraction of the brain. They're excitatory, and these are some of the cells that might be overactive in disorders such as epilepsy. Every one of these cells is an incredible electrical device. They receive inputs from thousands of upstream partners and compute their own electrical outputs, which then, if they pass a certain threshold, will go to thousands of downstream partners. And this process, which takes just a millisecond or so, happens thousands of times a minute in every one of your 100 billion cells, as long as you live and think and feel. So how are we going to figure out what this circuit does? Ideally, we could go through this circuit and turn these different kinds of cell on and off and see whether we could figure out which ones contribute to certain functions and which ones go wrong in certain pathologies. If we could activate cells, we could see what powers they can unleash, what they can initiate and sustain. If we could turn them off, then we could try and figure out what they're necessary for. And that's the story I'm going to tell you about today. An odyssey where we've gone through, over the last 11 years, through an attempt to find ways of turning circuits and cells and parts and pathways of the brain on and off, both to understand the science and also to confront some of the issues that face us all as humans. Now, before I tell you about the technology, the bad news is that a significant fraction of us in this room, if we live long enough, will encounter perhaps a brain disorder. Already 1 billion people have had some kind of brain disorder that incapacitates them. And the numbers don't do it justice, though. These disorders, schizophrenia, Alzheimer's, depression, addiction, they not only steal away our time to live, they change who we are. They take our identity and change our emotions and change who we are as people. Now, in the 20th century, there was some hope that was generated through the development of pharmaceuticals for treating brain disorders. And while many drugs have been developed that can alleviate symptoms of brain disorders, practically none of them can be considered to be cured. And in part, that's because, if you think about it, we're bathing the brain in a chemical. This elaborate circuit made out of 1,000 different kinds of cell is being bathed in a substance. And that's also why perhaps most of the drugs, if not all on the market, can present some kind of serious side effect, too. Now, some people have gotten some solace from electrical stimulators that are implanted in the brain. And for Parkinson's disease, cochlear implants, these have indeed been able to bring some kind of remedy to people with certain kinds of disorder. But electricity also will go in all directions, the path of least resistance, which is kind of where that phrase in part comes from. And it also will affect normal circuits as well as the abnormal ones that you want to fix. So again, we're sent back to the idea of ultra-precise control. Can we dial in information precisely where we want it to go? So when I started in neuroscience 11 years ago, I had trained as an electrical engineer and a physicist. And the first thing I thought about was, well, if these neurons are electrical devices, all we need to do is to find some way of driving those electrical changes at a distance. If we could turn on the electricity in one cell, but not its neighbors, that would give us the tool we need to activate and shut down these different cells to figure out what they do and how they contribute to the networks in which they're embedded. And also, it allows us to have the ultra-precise control we need in order to fix the circuit computations that have gone awry. Now, how are we going to do that? Well, there are many molecules that exist in nature which are able to convert light into electricity. You can think of them as little proteins that are like solar cells. If we can install these molecules in neurons somehow, then these neurons would become electrically drivable with light, and their neighbors, which don't have this molecule, would not. There's one other magic trick you need to make this all happen, and that's to really get light into the brain. And to do that, the brain doesn't feel pain. You can put, taking advantage of all the effort that's gone into the internet and telecommunications and so on, optical fibers connected to lasers that you can use to activate, in animal models, for example, in preclinical studies, these neurons and to see what they do. So how do we do this? Around 2004, in collaboration with Geert Nagel and Carl Dijsselrath, this vision came to fruition. There's a certain alga that swims in the wild, and it needs to navigate towards light in order to photosynthesize optimally. And it senses light with a little eye spot, which works not unlike how our eye works. In its membrane, or its boundary, it contains little proteins that indeed can convert light into electricity. So these molecules are called channelrhodopsins, and each of these proteins acts just like that solar cell that I told you about. When blue light hits it, it opens up a little hole and allows charged particles to enter the eye spot, and that allows this eye spot to have an electrical signal just like a solar cell charging up a battery. So what we need to do is to take these molecules and somehow install them in neurons. And because it's a protein,